Okay, all right. So we're going to start. There's a possibility we might finish 4 sections of the book today. Reason being that the first couple of them are really quite short, and I thought about making them a single section, but anyway, so we're done that. So before we go on, let me give you a little bit of context. So just a reminder, we've already talked about a bunch of sections of the book. We've talked about, the fundamental theorem of line integrals, and then Green's theorem, and then Gauss's divergence theorem, and Stokes's curl theorem. Right? And all of those theorems, by the way, combined with, I guess in the intro we talked about the fundamental theorem of calculus. These 5 theorems, arguably 6 if you consider that there are sort of 2 versions of the fundamental theorem of line integrals. There's the R2 version and the R3 version. 6 theorems, arguably, all have the same pattern, right? When I was making decisions about what topics to include in what sections, my goal along those lines was to let's try to give as much focus as possible to that pattern. Right? I wanted to show how the development of those theorems follow the same sort of strategy, and how the way that the diagram chase that they correspond to on the diagrams follows the same pattern. So I wanted that to be the focus. And then, of course, obviously I'm going to do some examples and applications and stuff like that. But there's other things to say about the fundamental theorem of line integrals. Likewise, there's some other things to say about Stokes's curl theorem. And these could have fit in with those earlier sections. Most books do put the stuff that I'm about to tell you in those earlier sections. I pulled them out because I wanted to leave more room for the things that we have talked about so far to see those comparisons between those specific analogous facts. And then along those same lines, the 2 topics that I'm going to start with today, path independence, and the next section is surface independence. Those topics, if I were to fit them in where they fit with the other, with the big boundary theorems, they would have been pretty far removed from each other. Separating them out like this, I can have them back to back, and that will help make it clear what the analogies are between these. So I think there's more pattern to notice. There's more analogies to notice doing it this way. Nevertheless, just full confession, so this is a little unusual. Okay. All right, so I want to look at this equation. Here it is, fundamental theorem of line integrals. You all remember this. And there is something a little weird about this. And that is, we look at this integral here. Now, this integral is defined on a curve C. In order to compute this integral, you should have to do calculations that, in fact, this is adding up over the entire curve. Shouldn't you, I ask rhetorically, shouldn't you have to look at the entire curve, the whole progress of the curve? We have terms that are being added up over the entire curve. Shouldn't you have to actually look at the entire curve to compute this thing? And, according to the fundamental theorem of line integrals, you don't. Fundamental theorem of line integrals says, nope, just look at the endpoints. So that's really weird. We have a calculation that's being done over that entire curve, and I don't need to look at any of this stuff at all. I just have to look at these 2 endpoints to actually compute it. And I find that quite mysterious when you say it that way. All right. Okay. Of course, the way we resolve this is that this is a very special integrand, the gradient of f, right? It's a trick integrand, right? Where as you move along the curve, technically you're writing down, terms that are defined, computed on each little piece of the curve, but because it's a gradient, what you're really just keeping track of is progressive change. And so, of course, when you're done with the integral, you just get total change, and total change is computed by looking at the endpoint. So it's not really surprising, but you say it a certain way, and it kind of seems to be. Now, let me say it a slightly different way, and that is, since this calculation over this curve is computed based only on what's happening on the endpoints, if I were to pick a different curve with the same endpoints, Well, it's got the same endpoints. It's going to compute the right-hand side the same way. Therefore, the values of these two different line integrals will be the same. Right? Let's see. How much you have C, buddy? There you go. Okay. That didn't last long. So the values of the line integral don't really depend on which of these two curves you pick. In fact, you could take that curve or that curve. All right? Doesn't matter. Suit yourself. Okay, hang on just 1 second. I gotta get Jack settled. Okay, lie down, buddy. Lie down. Lie down. Okay, there you go. Okay, lie down. Okay, there you go. Okay, that's nice. Okay, stay. Okay, see how long that lasts. Okay, so this is the way that we think about a new property of a vector field that I want to talk about called path independence. This vector field, and keep in mind, for this theorem to work, we had to use a trick vector field, right? But this vector field, gradient, has the feature that you can kind of pick any path you want. Suit yourself. It doesn't matter what path you take. I mean, it matters where you start and where you end, of course, right? But the choice of the path between that starting point given and that given ending point, the choice of the path in between doesn't matter. So we call this path independence. And here we go. Path independence says as long as, here let me color code a little bit better. This vector field is said to be path independent if, as long as the two curves that have the same starting point and same ending point, you're going to get the same value for the line integrals. All right. So what a odd, kind of fascinating property for gradient fields to have. Right? Pick your favorite path. Doesn't matter. Who cares? Any path you like. It's nice. So this kind of makes one naturally want to ask a related question. Hey, neato, are there any other vector fields that have this property? What if there are other vector fields that aren't gradients, but for a different reason, some other trick, have this same property that, look, as long as the starting point and ending point are well defined, pick your favorite path in between, and who cares? It doesn't matter. Wouldn't that be nice? That does not happen, as it turns out, and I'm not going to go through the discussion of why. It's, we just don't quite have time for it. Not really important for Math 212, but not only is every gradient path independent, but furthermore, every path independent, we're assuming everything in sight's continuous, by the way. Every path independent vector field is, in fact, a gradient of some function. Even if you don't know what the function is, it's gradient of something. Okay. All right, so let me show you a quick application of this, and this is not really the main reason we care about path independence, but it's a starter example. Suppose you know very little about your vector field. All I know is it's got components P, Q, and R. Not much to know. And I know that the P function has a factor of Z in it. Right? That's all I know about the vector field. Correction. That is all I know about the equation for the vector field. The one other thing I know about the vector field is that it is a gradient, but I don't know what that gradient is, what that anti-gradient is. Okay. And I want to compute a line integral. The curve C here, I know the curve. In fact, I have a parameterization of the curve. Now, of course, our first instinct of the, chronologically first a method that we know for how to compute this line integral would be to take this parameterization and brute force it. Right? Chapter 5, plug and chug. Except we can't, because I don't know what these functions are. I don't know what this R function is, and I don't know what Q is, and I don't know what this little P is, and I don't know the anti-gradient, so I can't plug and chug. All right. Here's the point, though. We know that our vector field is a gradient Therefore, we know that our vector field is path independent. And therefore, I am at my liberty to change this path to any other path that I like. I mean, the sky's the limit. Pick your favorite path, with the requirement, of course, that the starting and ending points don't change. So, I mean, that really would be asking too much if you can really pick any path, right? But keep the starting and ending points fixed. So let's look at what we've got here. Our curve here, our path is this, and I can plug in t equals 0 to see the starting point of this, and I get 0, 0, 0, and I can plug in t equals 1 into that parameterization, and I get my ending point e comma z 0 comma 0. And now let's think about the path I'm going to choose. Let's draw a quick picture of what we're looking at here. We've got, here's our XYZ axis system, and this curve starts there and it ends there. Now in between, it goes off and it does all sorts of, maybe whatever. I haven't got the slightest idea. It's a pretty wacky parameterization there, but it starts at that point and ends at that point, so it's doing something kind of like that, maybe. What is our favorite alternative path that starts and ends at those same 2 points? And everyone has different preferences, I suppose. I have a pretty strong preference for the straight line path, like this, to use instead. Note it's got the same starting point, same ending point, right? And it's easy to parameterize. I suppose there's different you could parameterize instead by t comma z comma t comma 0 comma 0, and then have t go from 0 to e. Suit yourself. Okay. So let's do that and see what happens to our parameterization. Parameterizing, there's our derivative, x prime, right? That's part of my dx vector is x prime dt. And the vector field, keep in mind we were given a formula for the vector field. F is this formula right there. And pretty quickly then I noticed that those zeros really come in handy, right? Those zeros make those last two terms in the dot product disappear, and I'm left with just that. And so I have a kind of a handy single variable integral there. And then the very last point, come back and notice that on my new curve here, on this curve, notice that z is always 0. That entire curve is in this z equals 0 plane. So because I'm doing a calculation on which z is always 0, I get to plug in z equals 0 into that integral. That makes the whole integral 0, and we're done. We really didn't have to do any actual calculations at all. What happened? Everybody happy? It's a neat trick to be able to just, I think I'll just change my curve. Right? It's almost too good to be true. I mean, think back to change of variables. It's the one other place where we've actually seen where you can take an integral defined on one domain and you can change the domain, but there's a lot of sort of catches when you're doing change of variables, right? You've got to compute that stretching factor and you got to rewrite blah blah blah. Here we just I think I'll change the domain. Pretty nice. Okay. So I want to talk a little bit about a related notion of physics that relates to path independence, aka gradients. I'll try to be quick with this. But physicists take a different point of view on path independence. And here's their point of view. One thing that you can do with line integrals, don't forget, is that if you have a starting point and an ending point, right, a line integral of a vector field computes work if that vector field is thought of as representing forces. Right, that dot didn't show up very well. Let me emphasize. There we go. Okay. All right. So now, what is work? Work has units of energy, right? So another way to think about this is that this line integral says, well, how much energy does it take to move from that point to that point? And are y'all? Hopefully, y'all have had if you haven't had a class in mechanics, no big deal. Hopefully, y'all have had a high school course that has the word physics somewhere in the name, like physical science or something like that. And hopefully everybody knows the idea of potential energy. Right? So potential energy is the mysterious place that the energy goes if I lift something up to a higher altitude. Well, I just expended a bunch of energy. Where did that energy go? Well, it's stored now in the form of gravitational potential energy in the remote control. Right? And then if I let go of the remote control, it will come hurtling down really fast. Now, where's all that potential energy? Where did that potential energy go? Well, it got down here, and it was moving fast. So when it got down to here, it had kinetic energy. Right? So energy never really goes away; it just sort of transforms into different forms. It's the idea. Right? Okay. So here's the problem. If we want to be able to talk about potential energy, gravitational potential energy specifically, the amount of work that it takes to move from this point to this point has to actually be well defined, independent of how I do this, but just based on the points. If I want to be able to talk about potential energy at that location, then only the location should matter in terms of defining potential energy. Well, here's the thing. I could get this remote control from this point to that point by a straight line path, or I could, in fact, get there by a curved path like that, or maybe some wacky spiral path like that. Look, if there's going to be a well-defined amount of potential energy, then the amount of work that I expend should be independent of which path do I take to get there. Right? So the very notion of potential energy, again, we're talking about gravitational potential energy here. That very notion of potential energy hinges on the idea that the vector field, that the gravitational field, is path independent. No path independence? I don't know what you're talking about potential energy. Right? Potential energy would not be something that you could define at a location. So that's kind of a big deal, and before I go on with the next observations here, let me point out that sometimes the reason ideas are important is not because they're computational tools, but the reason ideas are important is because, well, they allow us to come up with other ideas, which connect to yet further ideas, and those are computationally important. Right? So this is kind of what we're seeing here with path independence. Path independence, interpreted in the context of work line integrals of the gravitational field, give rise to the idea of a concept in physics. I didn't just compute anything, right? But I've got a new concept called potential energy. And by the way, it's only when you have that concept of potential energy that you can talk about how potential energy plus kinetic energy is a constant, and talk about another important concept of physics, conservation of energy. Not in the ecological sense, right? But in the mechanics sense of potential energy plus kinetic energy always stays the same. So big ideas that came out of this idea. Okay, so because of these connections, by the way, another little bit of terminology, path independence, aka a vector field being a gradient. Sometimes these gradient fields, path independent fields, are called conservative. Conservative meaning that they are vector fields with which I can define a related notion of conservation of energy. Okay. So anyway, that's how you're going to see it in a physics class. So they're going to talk about conservative vector fields. They might not say path independence ever. They'll say conservative. Okay, related to this, and I don't want to get too far into the physics, but this function, the anti-gradient function, this thing right here, that is the potential energy function in the physics context, as it turns out. And so the terminology is, instead of anti-gradients, sometimes, in fact, usually physicists will talk about the potential function of a vector field. They mean anti-gradient. And sometimes there's an issue with minus signs. This is a little bit of an annoyance, but forces point in the direction where energy is decreasing. Gradients point in the direction of fastest increase. So sometimes they'll refer to negative f as being, depending on how they want to treat the minus signs, they might use negative f as the potential function. But anyway, that's a context thing. Okay. All right. How's he doing over here?
Oh, he's fine.
Okay. Was I hearing some squeaky whimpers? Yeah, okay. All right. Well, he's fine. Okay. All right. How are we doing so far? Is everybody on board so far? Okay. So here's a related idea, kind of surprisingly related, as it turns out. And I'm going to look at this picture up here. So let's consider a scenario where we have a couple of points, x1, x0, and x1. And let's consider a couple of curves that start and end at that same point. Kind of what we're doing here, right? Well, I'm going to say usually that means that there is a surface. Actually, there's a bunch of surfaces, but let's think about one of these surfaces here that's kind of in between, if you will, these two curves. Now, there's a lot of different such surfaces, if there's any, right? Because I can take such a surface and I can kind of, poke it with my finger and kind of push it into the page a little bit, or kind of pinch, grab it and pull it out of the page. There's a lot of sort of flexibility in here. But it doesn't matter which one, just pick, any such surface. Quibble. How do I know that such a surface exists at all? Technically, there are some counterexamples, right? So let's look at this very quickly, and then we're going to not worry about it. It is entirely possible that one of the curves could tie itself in a knot, or maybe both of the curves tie themselves in drastically different knots, and there's some sort of just knot-related ugliness. That means that there kind of isn't really any such surface, right? This kind of a problem, this appears to be a serious problem. I'm going to say with a more sophisticated and proper treatment of the ideas I'm about to show you, turns out, I can't give you the details, turns out this isn't really a problem. Okay, so I'm going to ignore this. I claim it's not a problem. I claim it can be dealt with just fine. So I acknowledge the existence of this scenario, and it's not something we need to worry about in Math 212. Okay, so we're going to consider this scenario here, and let's see, I'm going to go over to where I have it drawn a little bit bigger here. And let me remind you, we've got this surface here, and we've got these curves C1 and C2, and we've got these starting and ending points x0 and x1. Okay, all right, so first observation I would like to make is that these two curves have the same boundary. The boundary of C1 is equal to the boundary of C2. Sure they do, right? What's the boundary of C1 is, well, it's these points, x0 and x1. This is the endpoint positive oriented. This is the starting point negative oriented. What's the boundary of C2? Well, same start point, same end point, both same orientations. It's the exact same boundary. Okay. All right. Next observation I want to make. Let's talk about the boundary of S. By the way, S I'm intending to be oriented onward. So what is the boundary of S? And think about, ignoring orientations momentarily, the boundary of S is these curves, C1 and C2. But with what orientation? Well, think about your swirls. And so it's going to be C2. We're going to be going this way around C2, but then that way, kind of backwards around C1. So the boundary of S is C2, C2 minus C1. And this is a little bothersome, that minus sign. How annoying, right? This minus sign seems to suggest, I made a silly choice about the orientations of C1 and C2. This C1 really should have been oriented the other way, right? So look, you could fix it. If I just change the arrow on C1 and make C1 oriented back this way, then I would very happily have a plus sign here. And I'd feel really good right up until I noticed, now because C1 is going back that way, now C1 and C2 don't start in the same point. They don't end at the same point. One of them starts where the other one ends, and the other one ends where the other one starts. Which means I would have a minus sign here. Right? So this is a whack-a-mole situation. That minus sign is there. You can't make it go away. You can make it move from here over to there, but it's not going to disappear. Right? So that minus sign is unavoidably part of just the geometry of space. It's a real thing. It's not a mistake. How we doing? Everybody on board? Okay. Alrighty. So with that setup, I'm going to apply Stokes's curl theorem to S. And here it is. Stokes's curl theorem applied to S. Line integral around the boundary of S is the flux through S of the curl of that vector field. Okay, come on, buddy. Come here. Okay, lie down. Lie down. You can do it. Come on, lie down. You want to lie down? There you go. Okay. Everybody on board? And now, as we've just discussed, the boundary of S is C2 minus C1. So boundary of S, C2 minus C1. And I could rewrite this line integral as the difference of those two line integrals. And so just a quick rewrite then of Stokes's curl theorem is that is equal to that. And this turns out to be a really powerful little arrangement that we've created. And here goes. Let's consider a scenario, hypothetically. Suppose that I had a vector field whose curl was 0. Let's just say. Pretend like the curl is just constant 0 everywhere. Well, here's the thing then. If the curl is 0, that means this flux is obviously 0. Right? The flux of 0 is going to give you 0. Well, if this is 0, that means that this right-hand side is 0. That means the difference of these two line integrals is 0. That means that these two line integrals, C1 and C2, are the same. And furthermore, not only are these two line integrals the same, but whatever surface I picked, right? Whatever two starting and ending points, whatever two curves I picked between them, those two line integrals would always be the same. That means that this vector field has this amazing property that as long as you pick two curves that have the same starting and ending point, you get the same value of the line integral. In other words, this is one of those trick vector fields. This vector field's path independent. And we already know that path independent vector fields are gradients. Okay, so curl equals 0 implies path independent. And the argument reverses very nicely. If the vector field is path independent, then whatever your setup is, these two line integrals are going to be the same. That means this difference will be 0, which means that this flux will be 0. Now wait a second. How could a flux be 0 through any surface, no matter what the surface is. This integrand, the curl of f, must be 0. So not only does curl equals 0 implies path independent, but path independent implies curl equals 0. Okay, so it's a pretty neat argument there, and notice that this sort of supplements what we already knew. We already knew that gradient and path independent were simultaneous. Again, now, by the way, I can't emphasize enough, we are assuming that everything in sight, every vector field, every function is defined and continuous everywhere. Things do get weird if you have a discontinuity. Things get surprisingly weird, so it's very important everything's defined and continuous, differentiable everywhere. Okay. So we already knew this connection. Now we have this connection, and so really we have 3 completely different properties that apply to all of the same vector fields. So gradient fields, aka conservative fields, are the same as path independent fields, which are the same as vector fields whose curl is equal to 0, and keeping in mind that curl represents the extent to which the fluid is kind of, that there's kind of a rotating of the fluid around some sort of an axis. If that curl is 0, we use the word irrotational. So we now have, roughly speaking, 4 synonyms to capitalize on. So gradient, conservative, path independent, irrotational. They all mean pretty much the same thing. All right. Everybody on board? Okay. All righty. Moving along to the next section. The next section is called surface independence. I'll make a quick confession about how I wrote a sizable fraction of this section. A sizable fraction of this section I wrote by going to the previous section, and I marked like almost a huge fraction of the previous section, and I did a copy paste, and then I did find and replace on various words. Right, but the pattern is that strong. It's an extremely strong pattern. The difference is going to be now. Let me come over here to our diagram. The difference is going to be that it's different things playing different roles. Roughly speaking, we are going to move over 1 notch on the diagram. So let me first, before we go along with surface independence, let me draw you a diagram chase of what did we just talk about with path independence. So there are certain special vector fields that we were talking about. We're talking about vector fields that are gradients of something. So gradient fields. And then we formulated this in a different way, though. We talked about how, gradients have this property of path independence. In other words, that vector field has the feature that if you take 2 different curves that have the same boundary points, then these line integrals over those 2 different curves will always take the same value. So this is my little diagram representation of path independence. Okay. Well, then, last thing we observed is that these same vector fields which are gradients, vector fields which are path independent, those same vector fields, their curl is 0. Yeah. Okay. So that's what we were just talking about. Now let me show you what we're about to talk about here with surface independence. It's this. It's that strong of a pattern. Okay, it's the same ideas. We're going to talk about vector fields which are, they're not gradients, they're curls of other vector fields. We're going to define an idea called surface independence that says if you have 2 surfaces with the same boundary curve, those two surfaces, over those two surfaces, this vector field will have the same two values of flux. And what we're going to find, and again, I'm just kind of giving away the game here, what we're going to find is that these vector fields also have the property that their divergence is 0. And all three of these properties, again, with all regularity assumed, all three of these properties are simultaneous. So it's a really strong pattern, and you're going to notice a lot of familiarity in the arguments that we're about to make, talking about surface independence. I encourage you to, have the book open to kind of, both different sections at the same time, and as you're reading along in surface independence, flip back and look at the analogous page in path independence and notice that, here, let's see here, two surfaces with the same boundary curve. That's kind of like when we had two curves with the same boundary points. And we're not looking at line integrals over those curves, we're looking at fluxes over those surfaces. And notice how everything, all the ideas, anything you understand about path independence, shift over one step on the diagram, that's something that you should understand about surface independence. Okay. All right, so that's the giveaway. Now let's actually go through and do it. So surface independence. Let's look at Stokes' curl theorem. Oh, by the way, that's one thing I forgot to put on the diagram here. Let me move this back real quick. We started off, this whole idea of path independence came from looking at the fundamental theorem of line integrals. Okay, so we are going to start our discussion of surface independence by looking at, the diagram kind of suggests this. We're going to start by looking at Stokes' curl theorem and notice the same kind of a pattern. Okay, right. So there it is, Stokes' curl theorem. Hey, here's a weird observation. There's something special about curl fields. That's a trick field. These fluxes are defined by a summation that happens over the entire surface. It takes the whole surface, right? And this says that we can, even though this summation takes place over the entire surface, but we can actually do the calculation instead just on the boundary. Remember, we were saying exactly that. Drop down by one dimension, we were making those exact same sort of like, hey, check it out, observations about the fundamental theorem of line integrals. Okay, so this vector field, curl, has this lovely feature that the surface kind of doesn't matter. As long as you fix the boundary curve, pick any surface you like. Now, the picture looks different. Instead of two curves with the same boundary points, here we have two surfaces with the same boundary curve. And now we do have to be careful about orientations in the same way that the two curves have to start at the same point, end at the same point. Well, analogously, these two surfaces, they have to have the same boundary curve, and by which I mean the same oriented boundary curve. So these two surfaces have to be oriented in such a way that they induce the same orientation on that boundary curve. And that means that I'm going to say they both have to, as I have the picture drawn here, both of these surfaces have to be oriented upward. So think about thumbs and swirls, and these two orientations will give the same orientation on the boundary curve. Okay. So I want you all to see this picture and think that's just one dimension different from this picture. Right? Instead of two curves with the same boundary points that then kind of between them there is they're both part of the boundary of some surface. Now instead we have two surfaces with the same boundary curve, and then between the two of them, they are part of the boundary of a solid. Okay. All right. So, oh gosh, sorry, I just hit the wrong button there. Okay, so let's talk about surface independence. Again, we have this lovely feature here. These vector fields, amazingly, it doesn't matter what surface you pick. Pick any surface, as long as the boundary curve is fixed, you're going to get the same value of the flux. So let's write that down as a property. A vector field, whatever that vector field may be. Who knows? Maybe there are more such vector fields. We call it surface independent if, as long as these two surfaces have the same boundary curve, the fluxes are always equal. Okay. All right. Okay. So, and then, as we just observed, all curls have this property. All curls are surface independent. Again, immediate consequence of Stokes' curl theorem. If you have two surfaces that have the same boundary curve, they have the same boundary curve C, Stokes' curl theorem says that's equal to that. Stokes' curl theorem says that's equal to that. Therefore, these two things are equal to each other. Okay, so now it is harder to show. It is not Math 212 accessible to show that it goes the other way, but this is a true fact. Not only is every curl surface independent, again, we're assuming regularity. Always, everything's regularity. No discontinuities, no problems. Every vector field, every function, everything in sight is continuously differentiable, no problem. Not only is every curl surface independent, but every surface independent vector field is a curl. Okay. All right. So nice coincidence there. Let me show you an application. Let's suppose that we are given a vector field, and we want to compute a flux through a certain surface. Right? Now again, as always, you could certainly, plug and chug. Right? You could chapter 5 this problem. It's not hard to parameterize. After all, the surface is a graph. You could use the graph parameterization, right? And then take a deep breath and get your nose down in there and plow through it. Right? And it wouldn't even be that bad, I suppose. I mean, it's just polynomials. There's probably going to be some square roots that's showing up, but it looks kind of doable. Right? Okay, suppose about this vector field we know an additional piece of information, that it is a curl of something. I don't know what of. I don't know what this anti-curl is. But I do know that this is a curl. G is a curl of something. So, just like in the first example we did with path independence, because it's a curl, that means that it's surface independent, and because it's surface independent, I can take this surface and I can trade it for any other surface that I like, as long as I keep the boundary. I'm not allowed to change the boundary, of course, but any other surface between that boundary, take your pick. Right. So let's look at our surface here. Our surface has this equation, z equals as an upside down elliptical paraboloid. Right. That's this thing here. Specifically, we're looking at the part that's above the xy plane, right? So it's just what I have there. It's this. It's an upside down bowl, right? Sort of an oblong upside down bowl. Please do be careful. Make sure to not misinterpret what the surface is. Some students have a compelling need to feel like, the surface must be all of this, and, it's got to include this, too, for some reason. Absolutely not. Absolutely not. It did not say, the boundary of the solid. Right? This just said, look, we're going to take this paraboloid. Paraboloid is a surface. It's just a surface. There is no solid anywhere in sight here. We're going to take that surface and look just at the part that's above the xy plane, and the part of the surface that is above the xy plane does not just magically include that part of the xy plane, it's also. Right? We just take the appropriate part of the surface. Is everybody on board with that? The language is something you have to be very careful with. If you misread the language, you'll be looking at the wrong surface, and this is you can't reasonably expect to get right answers if you can't interpret what the question is asking. So be very, very careful with that. That is part of the problem, to correctly interpret what the surface is. Okay, so that surface. Let's talk. What's the boundary of this surface? Got this upside down bowl. The boundary is it's the where the slice took place, right? It's this ellipse here. That is the boundary of that surface. And now we got to think about orientations. Be careful, right? Our orientation on our paraboloid was upward. Right? That was given, upward oriented. So there's my upward oriented normal vector. Upward-ish, recall. Reminder, don't misinterpret and think that means that all normal vectors point exactly straight up. Of course not. Upward is just a way of distinguishing between the two different options of normal vectors. Okay, so let's think about orientations then on this boundary curve. Thumb, swirl. Think about the swirls. How do the swirls sideswipe? And we get like that. No? How we doing? Everybody see how that works? Okay, so now keep in mind, we've already agreed that we have because it's a curl, my vector field is surface independent. And because it's surface independent, I can take this surface that I was given and I can say phooey on that. I'm going to take a different surface as long as it has the same boundary curve. So here we go. I'm going to throw away that surface. Now that I have a clear picture of what the boundary curve is, that original surface, go away. I have no further use for that surface. And now I just get to pick whatever surface I like, any surface I want that has this curve as its boundary. And in the interests of self-preservation, I got an idea. How about we pick the easiest one? And I think that flat, solid ellipse in the xy plane. I think that's a pretty attractive idea, right? It's flat. That's nice. Everybody on board? Seems like a reasonable choice. But the records show, if you want, you could take a wacky surface like that, right? But why would you, keep your life simple. Okay. All right, so with this new surface decided on, here it is again. There's that surface. Oh, we got to be careful with orientations. What's the orientation on this surface? Well, the orientation has to be whatever orientation gives me that same orientation on the boundary, right? The fixed, non-negotiable boundary has to be oriented that way. So I got to think through now. There's two possible orientations I could give to this green surface. Which one makes swirls that sideswipe the correct direction to give this orientation on the purple boundary curve? And you just got to sit there and do like this and think about the swirls and think it through. And hope you can persuade yourself that the correct orientation is upward. Everybody on board? Here's another way you can think about this, by the way. I don't want to make this precise. I'm not going to state this as a theorem. But I think this is a pretty good, I'm going to call it a trick. Right? Here's a trick that you can use about orientations. Think about this original paraboloid that we had with its upward pointed normal vector, and think about what would happen if you were to just slowly, continuously deform it just kind of deflate, if you will. Just kind of let it kind of slowly drop down to this green solid ellipse here, right? In that slow deformation process, these normal vectors would kind of come along for the ride and turn into these normal vectors. So that's a good sanity check. That's not the rule. That's not anything official or precise, but it's a good way of, making good decisions. I'll say that. Okay, so we've got our new surface. Here it is. New surface. Z equals 0, by the way. Right? So this is easy to parameterize. And easy to see what the normal vector is. The normal vector is clearly 0, 0, 1. So life is good. Okay. So, as previously noted, we said fooey on the original surface. I don't like that surface. We're instead going to use that surface. I'm going to rewrite the flux in terms of the normal vector because I know what the normal vector is. Right. And now continuing to rewrite. Again, our normal vector was 0, 0, 1. The vector field. Now, the vector field, of course, hasn't changed. That vector field is still this same vector field. Right? This surface-independent vector field. And but this dot product becomes nice and easy. It's just xy. And now, so we have transformed our original integral over a curved surface of a vector field. I have now transformed into, in fact, a scalar line integral over a flat surface of a easy scalar valued function. And there's different ways you could approach this. I would prefer to just say, that's equal to 0 by symmetry. Right. I can think through the details of that symmetry argument. Notice that our domain is symmetric, and not only is our domain symmetric in multiple ways, but this function has odd symmetry also in multiple ways. So pick a way, right? Pick a symmetry plane, and make a symmetry argument. Everybody good? Okay. Going back to our diagram here. So we have presumed a curl, and we've made observations that come from Stokes's curl theorem, and we've concluded this idea of surface independent, and we've actually used surface independent now to compute a flux. Right? What is left to do is to make this connection about divergence. So my goal is to show that divergence is equal to 0. That's what the pattern seems to suggest anyway. So does the pattern actually hold? Can I go through and make the analogous arguments? Well, here we go. It's going to work out just fine. I am, however, going to, I like to be able to move back and forth between, I think that's the best picture that I have. Yeah. Right, let me keep this picture here. So recall the scenario we're considering. We have two surfaces with the same boundary curve, oriented boundary curve. And so these surfaces have orientations that induce that same shared boundary orientation. And again, you got to think it through with swirls and side swipes, right? That these are the two orientations that would give you this orientation on the shared boundary curve. Quick observation: note you could also, in this case, just for intuitive satisfaction, you could think in terms of taking this blue curve and kind of what would happen if you were to slowly push that blue curve up until it was on top of the green curve. Well, this normal vector up would slowly deform into that up. Does that make sense to everybody? So, satisfying, I'll say, that these are that this is what the picture looks like. Okay, and now let me remind you that not only do these two surfaces have the same boundary curve, right? Boundary of S1 equals boundary of S2, but between the two of them, they make up the boundary of a solid. Now that solid is going to be hard to, it's this, it's the big lump, the big potato that's in between there. Right, there's that solid. And let's see, did I give that a name? I guess it doesn't matter. Let me call that R for no particular reason. Let's see here. So the boundary of R consists of those surfaces S1 and S2. Now again, be careful. Think about orientation. What is the boundary of R? Well, it's S1 is the top part of the boundary. That's oriented correctly. But because that's outward, boundary of a solid means away from the solid. But the bottom part of the boundary of R is it's kind of S2, except as part of the boundary of R, I need it to be oriented downward because that's away from the solid, outward, you might say, right? Whereas S2 is oriented conspicuously inward, upward, into the solid. So it's not S1 plus S2. It's S1 minus S2. And there's that pesky little minus sign again, right? I mean, the analogy is just like it was in the case of path independence. We have this minus sign here. And again, consider, the urge to, okay, well, this minus sign just means that, I feel like I just oriented S2 the wrong way. Why don't I just take this S2? We'll just orient S2 downward. This becomes a plus sign. Everything seems good until you come back up here and ask, well, then do S1 and S2 still have themselves the same orientation on their shared boundary? C. And no, they don't. You would just make this minus sign move up here. Right? So this is another whack-a-mole of minus signs. You cannot make it go away. Don't think about this minus sign as being indicative of a bad choice. That minus sign is intrinsic to geometry. It's there. That's how space works. Right? So, learn to love that minus sign. Okay. How are we doing? Everybody on board? Everybody see the analogy? Everybody see how this is the same? I'm deliberately laying this on the page in a way that's highly suggestive of what we were just talking about with line integrals, with path independence. Okay. Alrighty. So, when we were looking at, let's see here, let me move, I've kind of made a mess of my picture here. Let me move it back. When we were looking at path independence, we looked at this little scenario that we had created. We looked at, in fact, let me clean up this. Let me do it like this. We had these two curves with the same boundary points, and then we considered a surface whose boundary was, I'm just going to say both of those curves, right? And to that surface, we applied Stokes's curl theorem, and that was how we drew a conclusion about what the curl was. So, how to proceed here in this new case? Let the diagram be your guide. You don't have to reinvent the wheel. The diagram tells us what to do. We have just considered a scenario with two surfaces with the same boundary curve, and we have just gotten through realizing that between those two surfaces, they make up the boundary of a region, and following the pattern, I guess we should apply Gauss's divergence theorem to that solid. And that's going to tell us, hopefully, that the pattern continues. That will tell us, hopefully, something about divergence of one of these special vector fields. So, look, again, I'm just following the pattern, right? Doing so. Let's see what we get. Here's our picture. We've got this solid R. Its boundary is S1 minus S2. S1 and S2 have the same boundary curve. Let's look at Gauss's divergence theorem. There it is. Gauss's divergence theorem applied to that solid R. Right? Note this boundary surface, boundary R here. The boundary surface, as we agreed on the previous page, is S1 minus S2. And so I can turn that flux into the difference between those two fluxes. And the argument goes through just as it did before. I've got a triple integral. I've got a difference of two fluxes. Let's think through the cases. What happens if the divergence is zero? Well, it's okay. If the divergence is zero, then this difference is zero. Well, this triple integral is zero, which means this difference is zero, which means these two fluxes are equal, which, suitably interpreted, means that this vector field G is surface independent. Right? So, divergence equals zero gives you surface independent. And you can turn it around just fine if a vector field is surface independent. These two fluxes are equal. Therefore, this difference is zero. Therefore, this triple integral is zero. How could a triple integral possibly be zero for every solid, no matter what solid you pick? The integrand, the divergence, must be zero. Yeah. Okay, again, notice the layout on the page, right? It's really, really similar. There was a lot of copy, find, replace. And then, I'll confess, I did have to go through and think about, changing the occasional comma or choice of words or a couple other little details. Not everything is perfectly analogous, but it was very, very find and replace, copy oriented. Okay. So, here's those three ideas. We already had made the observation that curls were surface independent and surface independent fields were curls. Again, assuming everything in sight is appropriately regular. Now we have this third formulation that these are simultaneous with vector fields whose divergence is zero. So now I want to go back real quick to this example that we did. And there's something about this example that's a little bit disappointing. We had a vector field given. We had a surface given. And we wanted to compute the flux. And that's a pretty natural scenario to consider. Here's your vector field, here's a surface, go. Compute that flux. What was unnatural about this example is that in addition to that, I was given this mysteriously. Where did this information come from? I was just magically given that, this is the curl of some unknown vector field. I don't know what it's the curl of, but it is a curl, It's like a bad plot device, right? How could that possibly have come about? How is this going to come about in my everyday life? So that's the disappointing thing about this example. So now let me remove that as a given. The example I'm going to do here, same example. Vector field, surface, no magic-free information from the wizard. Right? That, magic-free information. Hey, this is here's the key that you need to make it all work. Not given at all. Okay. All right. So we are going to make that ourselves. We are going to compute on our own what the divergence is. Right? We're going to take this vector field here, the given vector field, compute the divergence. Divergence is 0. And because the divergence is 0, I get to conclude that it is a curl of something, which I, in fact, don't directly need. I get to conclude what I really need, which is that this surface is surface independent. The vector field is surface independent. Yeah, everybody good? Okay, so this is a much more impressive example. Here we are not given free information mysteriously out of nowhere, implausibly. Here we prove everything we need as we go. Okay. So real quick, and then we'll take a break. I think there's an argument that says that at least as a computational tool, path independence and surface independence are not equally useful. I think surface independence is more useful. And I'll tell you why. Let's go back to the toolbox metaphor, right? We go through, we find a bunch of computational tools in this class, and I congratulate you. Great, here's a new tool for your toolbox, right? Okay. Here's the thing about tools. If you already have a perfectly functional screwdriver, another screwdriver, yeah, so I guess that's nice and all, but I already have a screwdriver, so I don't really need another screwdriver. I guess I'll keep it, but it's not like you really needed one, right? But if you have a toolbox full of screwdrivers, a hammer is great. It's a new tool. It addresses different problems, right? And so that's something that you really do have a use for. Okay, so let's look back at path independence and go a few pages back here. Path independence. This idea of path independence. Hey, that's kind of neat. And if you have a vector field that's path independent, yes, it's a nice tool. I can change the path. It could be helpful in computation sometimes, but I already have a tool. If I have a vector field that's path independent, then it's a gradient of something. And we've got an awesome tool for how to compute line integrals of gradients. It's the fundamental theorem of line integrals. It's awesome, right? So, if you wanted to be a cynic, if you wanted to be a downer, you could say, who needs path independence? Anytime you could apply path independence, you could also apply the fundamental theorem of line integrals, which is awesome itself. So this is like a second screwdriver, and so it's kind of disappointing in that sense. See what I mean? Okay. So yes, okay. Now let me defend path independence real quick. Not everything is about computing stuff, right? So one of the big successes we had with path independence connects directly to motivating the idea of conservation of energy. So it's a very important thought that connects to other very important thoughts that then allow you to compute things. Right? So I'm not dissing on path independence. I'm just saying as directly as a computational tool, it's not a powerful computational tool as far as what we really need. However, surface independence. Whoops, where did my thing go? Here it is. Surface independence. It really is. This is really powerful because let's try to make that same counter argument of, if it's surface independent, that means that your vector field is a curl. Why don't you just compute the anti-curl and use Stokes' curl theorem? Answer. We don't know how to compute anti-curls. It's hard. I didn't give you any tools for how to compute anti-curls because it's something that's beyond Math 212. I can't show you how to compute anti-curls. Right, so surface independence is your first hammer, in a sense. And therefore, arguably, could be argued, surface independence is more important as a computational tool than path independence. Okay. All right, that's a good stopping point. We will pick up with the next section after the break. See y'all at 11:25. How about that? See you at 11:25.